So in this video, we're going to discuss integration, and this is just the reverse of differentiation. So the first thing we're going to do is look at the first method. So method one is simply the reverse power rule. So we have something that looks like this. Then we have dx. This is the same as ax plus 1, then divide by the new power, then plus a c this side. So whenever we are integrating, we just want to increase the power and divide by the new power that we have gotten, and we always add a constant, because remember this, if you are differentiating y is equal to x squared plus 3, if you are differentiating this, the answer is just going to be what? It's just going to be 2x. The same applies if you were to differentiate something like this, plus 5. The derivative also here is just 2x. You see that despite the constants being different, their derivative are the same. The derivative of this function here, this function and this function are giving us the same, but they had different constants. So no wonder when we integrate, we always accommodate the possibility of having a constant, and that constant could have been anything. No wonder we put a c at the end. So this can be explained with a practical illustration of this question here. So these questions here are what we can apply what we're from learning. Same applies with this, all these three. So this and that, all these questions here, even that, they just need the power rule, just this whole rule that we're saying, method 1. That's what we apply. So I'll give you an illustration. So you have, let's say, x to the power 3, then plus 4, x to the power negative 2, minus 5, x to the power 6, for instance, then minus, or let's say plus 10, then dx. So on integrating, this is going to be x to the power 4. We add a 1 there, right, to the power, then over the new power, then plus, this is 4x. This is negative 1 divided by negative 1. This is the power 7 divided by the new power 7. This is just 10x, then plus a c, because the constant here had an x to the power 0, so we increased it. It's like this. So we increase this with 1, so that's going to be x, this plus 1 over 0 plus 1. That's how it comes about to be 10x. Remember, the derivative of 10x is just 10, right? So meaning the integral of 10 should be 10x. So integration reverses what differentiation did. It does the opposite. So I want you to be thinking about it that way. Yeah, so this will just give us 4. Then there is that minus a 4x squared, then minus 7 over this, then plus 10x, then plus a c. It doesn't matter whether the powers are fractions or not. So maybe let me do something a little bit interesting. Let me do this guy here. So there's x to the power 2 over 3, then plus there's a 4, x to the power 3. I think this is the same as x2 over 3, then plus a 4, 1 over x to the power 3, dx. This here is the same as x2 over 3, plus a 4x negative 3. So now we can integrate this. Increase the power by 1, that's going to be 5 over 3, then divide by 5 over 3, then plus. Increase the power by 1, it becomes negative 2, divide by negative 2, add a c this side. Then down, you're just going to have 3 over 5, x to the power 5 over 2, minus a 2, x to the power negative this, then plus a c. You get this. So this is what we call an indefinite integral if there are no numbers or no limits given. In an event where there are limits given, if they give you, let's say 1 and 2, let's say x to the power 2 minus x, let's say 3, something like this, we just get x to the power 3, then over a 3 minus 3, x to the power 2 over the 2. What you get, you don't add the c. When there are numbers here, these are the limits. This is called a definite integral when there are limits indicated. There are numbers, one on top, one at the bottom. So we put 1 there, we put a 0. In the whole function, we replace the 1. Wherever there's x, put a 1. That's going to be this to the power that, minus 3 over 2, 1 to the power this. Then put 0 wherever there's x, that's going to give us a 0. This will be 1 over 3 minus 3 over 2. This is going to give us a 6. Then this is going to be 2 minus 9. This gives us negative 7 over 6. We say units squared. That's what we write. Whenever there are numbers, meaning you have to compute the integral at those particular two numbers given. So this is just method 1. Method 1, which is also known as the reverse power rule, is only used when you have a polynomial or a linear, and it happens, or rather is used whenever something can be put in a straight line. Same applies here. So even this guy here can be written as 6 negative 2 then plus 4 x to the power half then minus 3x then plus what? Plus 2. So you see this, then you can integrate the rule here. The question is asking us to integrate it. So this is the only time when the power rule can, the reverse power rule can work, method 1. So here I'm just going to give you a summary of all the rules. Then a separate video is going to be made for both tutorial sheets for those doing Math 1120 and Math 1100 and 1110 to solve your questions. Yeah, so I'm giving you the methods here. So method 2 is by using partial fractions. So now here you have to learn partial fractions first. There's a video separate already that teaches how to resolve partial fractions. So here the rule that we're just going to be using is that whenever what's on top, whenever the numerator is the derivative of the denominator, the answer here is just going to be ln of whatsoever u is, then plus a c. For instance, the integral of 1 over x. This is the same as ln x, then plus what? Plus a c. So this should make sense to you. Let me give you an example. So here is a question. They're saying evaluate the following integrals using partial fractions. So I'm going to pick this case here, something that is easy to handle. So we've done partial fractions already in class. If you still have questions, there's a separate video. You can just check it out. It will teach you how to resolve partial fractions. So example, this is method 2 using partial fractions. They're saying what's the integral of x? Then down we're having x plus 2 and x plus 2 and x plus 3. This is dx. So the first thing you have to do is to resolve this. So pause the video and try to resolve this if you remember what we did under partial fractions. Okay, so this is just a over x plus 2 and b over x plus 3 because these are linear denominators, right? They're linear factors. This is just going to end up giving you x is equal to, there's a, there's x plus 3, and then there's a b and x plus 2. So from here, we solve the first denominator here, which is x plus 2 equated to 0. This gives you negative 2. Replace it wherever there's x in the function. It's going to be negative 2, which is a, negative 2 plus 3. This is going to be b, negative 2 plus 2. So this is just going to give you a. So already here a is equal to negative 2. Then we do the same as well to solve the next denominator here, which is x plus 3. So x plus 3 is equal to 0, meaning x is equal to negative 3. Put your negative 3 in this expression again. So negative 3 is equal to negative b. This is just going to give us b is equal to 3. So at least we have this. So the whole question now is as follows. So when they said x plus 2 and x plus 3 dx, they meant the same thing as negative 2 over x plus that, then plus, this is just a 3 over x plus 3, then dx. Because the partial fractions of this expression are these. We've gotten the a, we've gotten the b, because we equated them here. Remember we said this is equal to that, right? We know our a, we know our b. So now we're going to factorize, or rather separate them first. So let the integral symbol affect them independently. Then there's a 3, x plus 3 dx. then this is going to be, the negative 2 is factorized outside, leaving 1. The reason why we have to factorize negative 2 is that the guy on top, the numerator has to be the derivative of the denominator. So we have this 3, then integral of 1 x plus 3, then dx. This is going to be 2 ln x plus 2, then plus 3, and ln x plus 3, then plus a c this side. So this will be the integral of the question that was given. So this is how we use by parts, by partial fractions. So by partial fractions, it just comes back to the rule that the numerator has to be the derivative of the denominator, so that we can just say it's ln the u, then plus a c. So no wonder we had to make sure this is a 1, because the derivative here is 1 and the derivative there is also 1. That's the reason why we factorize the negative 2 and the 3 outside, because they're just constants. Yeah, so this is just method 2. So please watch all the 4 cases on partial fractions. Then method 3, this is U-substitution. So this is also known as reverse chain rule. Yeah, so this is reverse chain rule. So if you have a function with a weird power or a very big power, that's when you can think about U-substitution. So the same way that now when you look at questions, you're able to figure out the rule you're supposed to apply under differentiation, whether it's product rule if they're multiplying each other, quotient rule if they're dividing each other, chain rule if there's a weird power. It's the same thing even here. So U-substitution works if there is a weird power or a power that we cannot evaluate. Let me give you an example. Let's say we have, let me say 3x to the power 2, then minus 1. This is to the power 6, then dx. So whenever you have something that looks like this, we said whenever there's a big power or a weird power and there's integration, just know that it's U-substitution. You let the part which is raised to that big power or the weird power be called u. No wonder it's called U-substitution. So this is 3x squared minus 1, meaning the question has now changed. We're now having x u to the power 6, then dx. Because we're saying this whole part is u, right? That's the substitution we've made. So we can differentiate this. This is going to be du dx. This is going to be 6x. Then from here now, we're going to make dx the subject of the formula by cross multiplying and dividing both sides by 6x. So you're going to get dx is equal to du over 6x. So we're saying where there is dx in our new expression here, where there is dx, we can put du over 6x. You notice that the x and the x are going to cancel, leaving us with u to the power 6. Then there's a 6 down, there's a du. This is equal to, factorize the 1 over 6 outside because the 6 is at the bottom, so we assume it's 1 over 6. U to the power this, then du. This is now going to be the same as 1 over 6. Integrate this, that becomes u to the power 7. Increase the power by 1, then divide by that new power, then plus a c. This is just going to give us 1 over. We have 6 times 7. That's going to give us what? 36 by 6. That's going to be what? A 42. U to the power 7 plus c. We now replace u with what u was. U was just what? 3x squared, then minus 1 to the power 7, then plus a c. So we have integrated using U-substitution. This is basically what we were supposed to do. This is how we're supposed to handle the question. Hope this is okay. Yeah, so this is how U-substitution is done. Let me show you another one. This is taken from the Math 1100 tutorial sheet. So I'm going to do this question there and also this one there. Just these two are going to be enough. So the first one is, so let's call it example 2, U-substitution. Please take note on method 3. Yeah, so this is just the integral of x over, down there is 3x squared plus 5, 3x squared plus 5 to the power 4 dx. So we are still using U-substitution because there's a big power 4 that we cannot evaluate. So u is equal to the thing raised to a big power. So this is just x, then u to the power 4, then dx. From here, we're going to differentiate, that's du dx. This is going to be 6x. Then we can have dx is the same as du over 6x. So meaning, wherever there is du, u to the power 4, we can multiply this with du over 6x. So that the x can cancel, leaving us with du, then 6u to the power 4. This is the same as 1 over 6 outside. We have 1 over u to the power 4, then du. And this is going to be 1 over 6, integral of u negative this, du. This is going to be 1 over 6 u to the power negative 3 over a 3 plus a c. This is 1 over 18 u to the power negative 3 plus a c. We can write it back as 1 over 18 times 1 over u to the power 3 plus a c. This is 1 over 18 u3 plus a c. And we just write back what we had, 18 3x squared plus 5. So this is your 3x squared plus 5 to the power 3, then plus a c. So this is the integral of the question they're from asking us. This is how we would have done it. So this is how we apply. U-substitution. Let's do the last one. So you can pause the video and attempt this first before we do it together, so that you see whether you're following the steps or you're going to get the same outcome. So example 3. So integrate 2x squared, the fourth root, 5x3 plus 3, then dx. So we're going to let the inside part be equal to u. This part is the one that is having a weird power. So u is equal to 5x to the power 3 plus this, meaning the question now changes. It's now 2x to the power 2, the fourth root of u, then dx. This is the same as the 2x squared, u to the power 1 over 4, then dx. Then here we can say du dx is equal to, this is 15x to the power 2, meaning that dx is equal to du over 15x squared. This is the integral of 2x squared u 1 over 4. This is du, then 15x squared. This is just going to give us the same thing as the integral. The x squared cancels. We just have a 2 over 15 u 1 over 4, then du. Then here we can factorize the 2 over 15 outside. We have u 1 over 4, then du. This is equal to 2 over 15. Increase the power by 1. That's going to be what? That's going to be 5 over 4 divided by 5 over 4, then plus a c. So this is the same as 2 over 15 multiplying 4 over 5, then u, 5 over 4, then plus a c. This gives us what? This gives us 8 on top. Then down, if we multiply our 15 by 5, so we're getting a 75. Then our u, 5 over 4 plus a c. This is now the same as 8 over 75. Where there is u, we replace back what we had, which is 5x to the power 3. 5x to the power 3, then plus a 3. This is 5/4, then plus a c. So this is what we would have gotten using U-substitution. This is how U-substitution is used. Then the last rule that you have to learn in your first year under the rules of integration method 4 is integration by parts. So now I'm going to use something that's very simple. The formula that I'm going to be using here is that V U prime is equal to VU minus U and V prime. So some people say this is the same as V. They say du is equal to V, then U, then they'll say U, then dV. Yeah, so it's really up to you because the meaning is the same. It's just a different representation, but we try, it means the same thing. It's exactly the same thing. Yeah, so whenever they give you a question, you have to decide which portion of your question is going to be the V and which one is going to be the U prime. That's the first step that you're going to consider. So I'll give you simple examples. These, we did them in class. I'll just follow the same process we did in class. So this is just x and ex dx. I'll follow this one. The next one is the same as e. Let me say ln x, for instance, then dx. Yeah, then the last one, I'm going to give you something that's very interesting. Ex, and we have cos x, then dx. So, to begin with, the first one here is very straightforward. We have examples. So this is by parts. The first one, we're saying x, then ex, then dx. So we said according to the formula says the integral of v, then u prime, there's a u prime there, is equal to v and u, then minus u and v prime. That's a rule. So if I let this one to be, I choose this one to be my v, and I choose u prime to be my ex dx, the guy that was already differentiated. So if you want to move from v to get v prime, we differentiate. This is going to be 1. And if you want to move from u prime to u, we integrate. So the integral of this is just ex again. So the choices of v and u prime depends on the question. So you make the choices by choosing the one that you want to be v is the guy that becomes simpler when you differentiate it. We don't want something that becomes complicated. As we are solving, if the numbers or the expressions we're getting are becoming complex as compared to the question, meaning we have to reverse the choices. So if we choose this to be u prime and choose this to be v, meaning we would have to integrate this to get the u, because this is u prime, right? To get u, we have to integrate. It would have been x over x squared over 2, which is bigger than the question. So we're going to go with this choice. The selection here that we've made is okay, and we just substitute. This is the question. This is v times u, so v times u, that's x, ex and ex, then minus, this is this times that, because your v prime is 1, so it won't change anything. Yeah, so this is just going to be ex squared, then minus the integral of that is 2ex, then plus a c. So we're saying the integral of this is just this expression that we've gotten there. So the formula for integration by parts has an integral symbol in the question as well. So now we're having this part here. So this is the reason why we're integrating this part. So this is what we get. Yeah, so let's do the next one. So the next example is the integral of x, then ln x, then we have dx. So the v that we're going to choose here is x. The v has to be something that becomes simpler. So I'm going to choose this because we can integrate this. Then your u prime is just going to be x. So you realize that I've decided to make these choices because if I try to get this as my u prime, I'll be unable to integrate it. We don't have an exact integral of this. Yeah, so v prime is just going to be 1 over x. Remember how we integrate ln of something? it's that something, differentiate it, put it on top, then over that same thing. That's the integral of ln something, ln u. So this, when you differentiate it, it's u prime over u, right? Yeah, so now we're getting this. Then u, when we integrate this to get u, it's going to be x squared then over the 2. Then this is going to give us something like this that we're able to evaluate. This is equal to v times u, that's this, over 2, then ln x, minus the integral of this guy, u times v prime. It's u times v prime, then dx. This just gives us x squared over 2 ln x minus the x and the x cancels, we just have x over 2, then dx. This is the same as x squared over 2, then ln x, minus 1 over 2. I'm factorizing the half outside so that I just remain with an x. And this x here can be integrated. This is just ln x, 1 over 2. This is going to give us x squared over 2, then plus a c. This is the same as x squared over 2, then ln x, minus x squared over 4, then plus a c. So this is going to be the integral of the whole expression that we had, the x ln x dx. So this is how integration by parts works. We choose one to be the v, one to be the u prime, then we differentiate the v, then we integrate the u prime to get the u. Yeah, so this is what we always choose. Let me give you the last one. The last example we can do is ex, then we have cos x dx. So here if you choose v to be ex, then u prime to be cos x, meaning the v prime is going to be ex again. Then the u is simply going to be, when we integrate cos, we get sine. So this is going to be ex, then sine x, minus ex, then sine x. That's what we are having. So now if we get this part, this portion here, I'll put it in a different color. So this portion here also needs by parts as well. So I'm going to do it in green so that you see it. So this is ex, then sine x dx. When you use by parts, you can let the v the same order again. V is equal to ex and the u prime be equal to sine x, so that we can now get the v prime to be ex and the u, the integral of this is negative cos. So this is going to be, we're going to say what? We're going to say negative ex cos x. Then we have minus integral of this times that, that's negative ex and cos x dx. So this here is the same as negative ex cos x plus integral of ex then cos x dx. So the integral of this part that I've put in a box is this. This is the answer that we need to replace there. So if we may replace it there, I'll put this now in yellow. This is ex, then sine x minus the answer we're from getting. The answer we're from getting, we have to put it there. This is just your negative ex, then cos x plus integral of ex and your cos x dx. That's what we do. Then from here now we can proceed and simplify this whole thing. I'll raise this part. So now we are saying the integral of e cos x dx is equal to ex sin x plus ex cos x, then minus integral of ex again cos x. So you notice that the question has appeared on the right hand side as one of the solutions to the intermediate integration that we did. So I'm going to take this and make it cross over the other side. because they're like terms. So we'll say the integral of ex cos x dx plus ex cos x dx is equal to ex, then sine x plus ex and the cos x. So these are like terms, so they can add. That's ex, then cos x dx is equal to ex, then sine x plus ex and cos x. Divide by 2, divide by 2. This is going to give us ex, then we have cos x dx is equal to, this is ex sine x plus ex cos x over 2 then plus a c. So this right here is the integral of this whole expression. It was repeating itself, but we managed to manipulate it to make it the subject of the formula. So this is how we handle such a case. Okay, if this makes sense, try to attempt the following. So task is integration of something that looks like this, ex and sine x. Also the other one is ex squared and ex. So use by parts to integrate these two and submit to me on WhatsApp. So I hope this is okay. This is just like a summary of all the rules that you need. The separate videos about the tutorial sheets will be sent as well. So thank you so much for watching.